And then even worse is that the dressing for 2-qubit gates means you're going to intertwine stabilizers from distinct logical qubits, 2 different code blocks. And okay, so what I should say is we're not willing to allow arbitrarily far staggerings. We don't let the clocks get so far out of sync as that from one another. So just sort of by virtue of the number of these dress stabilizers we include, they let you stagger to a certain degree, and if you try to go any further, the code Hamiltonian blocks you with an energy penalty. And so you can now start to think of, we've taken the locality of the original stabilizers, which for the 6D color code no one has computed, but is several, k local with k equal to a few hundred. We've added a clock for each qubit, and now I'm saying that you might have to intertwine stabilizers from distinct logical qubits. So the support of these terms is, getting very high weight, but again, still constant. Okay, so yeah, okay, this is what I was saying, and this limit on staggering you could sort of think of as the speed of light in the space-time point of view. Speed of light is just going to be 1 for us. Okay, now just to say a bit about everything being unitary in a larger Hilbert space, this means that we're going to replace the projective measurements that you would ordinarily do with coherent unitaries that sort of see not the result of the measurement onto classical ancillas, which are coherent qubits but are only going to be used classically. And each physical qubit then for us is going to be measured by a classical wire. So the real key to this project is thinking in detail about what this ordinary fault-tolerant quantum laboratory really looks like. And so you have some wire that, the reason it's a wire is because you want the interaction with the physical qubit to be local, but you also want the classical wire to be highly stable. So it kind of, it measures the physical qubit and then quickly branches out in a tree-like structure to become a classical repetition code that will be stable at non-zero temperature. And yeah, so that's this point about the tip of the wire being very pointy to keep the interactions local and bounded in degree. And this classical post-processing that you do on the side is sort of global. So you have to take an entire code block, which is macroscopic, measure all of the stabilizers, feed them into some coherent classical computation that proceeds for an amount of time that scales polynomially in the size of the code block. And meanwhile, everybody else, the quantum qubits are just sort of waiting around. So they might be advancing their clocks, but nothing really interesting is happening. They wait around for the classical post-processing to be done, so then you can perform the conditional corrections or whatever you need to do back onto the quantum computational register. So now, yeah, let's take this 4D space-time view. And so ordinarily when we think of quantum error correction, we think of doing it actively. That is not this passive Hamiltonian terms that enforce you to be in a particular state, but you're going to actively measure stabilizers. And so the idea is that, so the observation is that there's no energetic protection on the qubits themselves. But when you do this in an ordinary quantum computing laboratory, you do have an energetic protection in the classical computer from the classical material science, or the material science of the classical computer. And so the point of this is that active error correction is possible because we take entropy out of the fault-tolerant quantum computer and dump it into classical self-correcting memories. The ancillas we get from the classical self-correcting memories are nice and clean, and this allows us to get rid of the entropy in our quantum computer. And so in our case, actually, for everything I've described, we don't really need the 6D color code. I put that there almost out of completeness and is sort of the way that I came onto this, but really all we're going to need is stable classical ancilla that are enforced by some classical Ising model repetition code, and you could just put nothing on the quantum register and just see that the gate terms are actually going to suffice to protect the quantum register. Okay, so you can do everything with the 6D color code, or you can you can sort of take this history state view of active error correction where you passively protect the classical ancilla, but you leave the quantum computational register unprotected. Okay, and so how can we begin to analyze this construction? So the entire Hamiltonian is unitarily equivalent so again, we're going to apply the same sort of unitary that we saw in the ideal ground state case, and it's going to undo the propagation Hamiltonian into a part that only acts on the clock register and sort of performs these continuous membrane updates, and then a part on the quantum register, which is just the static code Hamiltonian. So because we put in the dressing, the global unitary just undoes the dressing in just the right way. So the picture to have is that you have a membrane evolving along on the time register, and on the computational register, you just have a static code Hamiltonian. And so, hey, that's something we know how to analyze. These two systems are now actually completely independent. So another important step is that we want to understand the distribution along the time configurations, and to do this we're going to put time on a circle so that we can take advantage of symmetry. So you can imagine that you spend half the circle doing your computation and the other half just undoing it with the adjoint of those gates, and this means that by symmetry all of the valid time configurations will be equally likely in every eigenstate. So this is what we're going to use to understand the distribution along the time register to make sure you have a reasonable probability of measuring the output. So for the initialization, just put the classical ancillas in the logical zero state, turn on the Ising interactions. So this is the analysis in the rotated frame. So you just have some ancillas in a classical zero state. We already know that's going to be metastable with an exponentially long lifetime. And then we know that the thermal state of the clock has to be uniform along the circular time register. And so, and then also, so in this scheme where we're doing active error correction, you have the classical error correcting code on the classical ancilla, you have nothing on the quantum register, and so that's going to just be maximally mixed, and then you have this uniform mixture of states along the time register. Okay, so that's the picture to fix in your mind, and then now what's going to happen when we rotate back to the real frame? Okay, so when we're in the real frame, the diagonal elements of the thermal density matrix in the time register basis, right, so you're going to rotate back, which means you apply these unitaries, and because U is a fault-tolerant circuit, it's just going to coherently measure your maximally mixed state on the encoded qubits, and then dump that entropy into the encoded ancillas, right? So just by design, it behaves exactly as it should. So the correct operation depends on this. And so now, the argument for the thermal stability, so we were able to understand the thermal stability in the rotated frame because that's just a model that is well studied and well analyzed. But if you look at the Davies master equation and you assume weak coupling where this equation is valid, it really only depends on the spectral properties of the Hamiltonian. So the Davies master equation is kind of covariant with this global unitary, and the spectral properties of the Hamiltonian determine the, well, and the spectral properties of the bath, but the bath doesn't get rotated by this global rotation. And so in particular, sort of the spectral gap or any quantities that determine the convergence time of, or the thermalization time of this Davies master equation will be unaffected by this global rotation. So it's kind of interesting actually, you take local noise in the real frame, you rotate to the fictitious frame, the noise becomes very non-local, but the Davies master equation tells you that the thermalization time is the same. I like that argument, but also it's a little cheap in some ways. So I would really like to actually analyze the strong coupling limit of this noise because our hunch is that even in the rotated frame where the noise becomes very non-local, things will be okay because of the fault-tolerant properties of the circuit. And actually, just to say a little bit about control errors in the local Hamiltonian terms, so the difference between this W actual and W ideal is going to be small because W represents because W performs this fault-tolerant circuit. So even if you have some small errors in your gate terms, you can actually argue that those won't do any damage either. Okay, so the point is we've described universal quantum computation in a finite temperature metastable state of a K-local Hamiltonian. The check operators are very high weight but still constant. And the overall overhead in terms of the number of additional qubits and so on, you have to include all scales polynomially in the size of your original quantum computation. So the fact that we can get a 4-dimensional self-correcting memory by taking the history state of a 3-dimensional fault-tolerant quantum computing laboratory, to me, this relates the quest for planar fault-tolerant architectures with this open problem I mentioned of obtaining self-correcting quantum memories in 3 dimensions. So this is a new kind of 4D self-correcting memory apart from the toric code. It's very inhomogeneous. You have these different parts to it. It's not commuting and so on. Now, I would like to extend this construction, and I have ideas about how to do so, how to extend it beyond metastability to actually put the computation into the true equilibrium Gibbs state. I don't think that'll be spatially local. But the reason I want to do this is because my hunch is that deciding the thermal energy at system size independent temperature up to polynomial precision should also be QMA hard, right? So here's the true Gibbs state without any discussion of metastability. Here's the thermal energy, which generalizes the ground state energy, which we saw in the first slide. And the question is whether below some system size independent critical temperature, what is the complexity of estimating this thermal energy? And this construction could answer that if we can take our analysis beyond using these facts about metastability. Okay, thanks. Yeah.
So, using it sort of for the purposes of making us feel comfortable in the universe rather than building a quantum computer.
Sure.
Looks like you're getting to when you say metastable memory, this is one where the lifetime of the would be unbounded as you made the system larger.
Exactly.
It would not be as would not be an absolutely stable Gibbs state.
Yes, exactly.
But this last thing is tantalizing. You're hoping to get a Gibbs state at finite temperature of unbounded, well, let's say logical depth.
Yeah.
Even, yeah,
So
good.
So
Get that.
yeah.
What is the last thing you said about the finding the thermal energy is QMA hard?
Yeah.
But what's the difference between those two things and the rho sub beta and the E sub beta?
The difference between, I mean, that's the,
You were contrasting this. Say the last sentence or paragraph again.
okay. So it would be nice to say that estimating the thermal energy of a local Hamiltonian is QMA hard. And to do that, I want to have I want to talk about the true Gibbs state and not just a metastable thermal state. So that's sort of the connection. These are just the definition of the thermal state and the thermal energy. But so this point about how can we go beyond metastability. So there's a conflict that I understood most clearly yesterday for the first time between topological order and, so because topological order demands local indistinguishability, it's hard to force a topological code into one sector or the other using local Hamiltonian terms, right? But for our classical Ising models, we can do this. And now they sort of also end up forcing the quantum register into a particular state, right? So, so that's why it looks like it works. But the interactions on the time register are going to, I think to do this might require unbounded degree interactions on the time register, which is allowed in the Hamiltonian complexity game, but is not spatially local. So yeah, and it's also harder to analyze because, so to get this kind of result about either the true Gibbs state, you have to include this input term that breaks the symmetry of the time register. And so now the distribution over time steps of the computation becomes much harder to analyze. And if you want to get this result about the QMA hardness, you want the input term and the output term. And so that's kind of, that part's still in progress, how to actually analyze that, yeah.
Okay, if there are no more questions, then yeah, it's thank you again.
Thanks.